Lab experiment number 2, titled Gas Laws.
Gas laws are 4 laws that the gases obey
With respect to pressure, volume, temperature, and number of moles. Firstly, there is the Boyle's law, which shows that pressure is indirectly proportional to volume and vice versa. Secondly, we have Charles' law, which shows that temperature is directly proportional to volume. Thirdly, there is the Gay-Lussac's law, wherein pressure and temperature are directly proportional. Fourth, we have the Avogadro's law, where volume and the number of moles are directly proportional. And finally, there is the ideal gas equation, where pressure times volume is equal to the number of moles times the gas constant times the temperature.
The experiment aims for students to have a better interpretation of the mathematical and quantifiable relationships between the different properties of gas and gas law. Different procedures and types of experiments are done in order to get a better understanding and application of the gas laws.
There were 4 stations where 3 gas laws and the ideal gas equation were applied. Each station had an apparatus connected to a vernier LabQuest device, which was then connected to a laptop with a logger program. This enabled measurements of the 4 variables for experimentation.
In Station 1, the focus of the experiment was the relationship between volume and the pressure of a gas. This was done with a syringe setup where the volume of the syringe was first increased in intervals of 5 milliliters, then decreased in intervals of 5 milliliters, and the pressure was recorded accordingly. The data was represented by these graphs, and the values of K were found to be 19.89 in pushing and 6.83 in pulling, although these are subject to human error during the procedure.
In Station 2, the focus of the relationship was between the absolute temperature and the pressure of a gas. This was done with an Erlenmeyer flask and a water bath setup where the temperature of the water bath gradually increases and the pressure of the air inside the flask is measured accordingly in intervals of 10 Kelvin. The data is represented by this graph, and the value of K was found to be 0.0031. In Station 3, the focus was the relationship between the absolute temperature and the volume of a gas. This was done with a similar setup as Station 2, but with a syringe to test volume instead of pressure, and the data is represented by this graph, while the value of K was found to be 0.517. In Station 4, the focus of the relationship between the pressure and number of moles of a gas. This was done with an Erlenmeyer flask and syringe setup, and 20 molecules of air were let into the syringe and pushed into the flask, and this was repeated 5 times, and pressure was recorded each time. The data is represented by this graph, and the value of K was found to be 0.00624.
For Station 1, the relationship between volume and pressure, when temperature and number of molecules are constant, is inverse. When volume increases, pressure decreases proportionally. The equation is P equals K over V. This station showcases Boyle's law.
For Station 2, the relationship between pressure and absolute temperature, when volume and number of molecules are constant, is direct. When the temperature increases, pressure increases proportionally. The equation is P equals K times T. This station showcases Gay-Lussac's law. For Station 3, the relationship between volume and absolute temperature when pressure and number of molecules are constant is direct. When the temperature increases, volume increases proportionally. The equation is V equals K times T. This station showcases Charles' law. For Station 4, the relationship between pressure and number of molecules when volume and temperature are constant is direct. When the number of molecules increases, pressure increases proportionally. The equation is P equals K times N. When one transforms the 4 equations from the 4 stations into proportionality form, it is possible to combine them based on the equations of pressure and the other 3 variables. The result of this is P is directly proportional to N times T over V. And when this ideal gas law is transformed into ideal gas equation, replacing proportionality symbol with a proportionality constant, K, then rearranging the variables, the equation is PV equals N times K times T. This is the ideal gas equation, where all 4 variables from this experiment are combined into one equation, with K as a proportionality constant.
Our group will be able to apply our learnings and information from this experiment when it comes to things such as aerospace studies, because all properties play an important role in navigating planes and transports in the Earth's atmosphere.
Some challenges we faced included the human error in our Station 1 data, which caused the mathematical relationship derived to be a bit skewed. In order to properly derive conclusions, we need to be more careful in the future while performing precise procedures. Another challenge faced was in Station 3, when the apparatus was not working like it was supposed to. The volume reading was not changing even if the temperature was drastically increasing, which is not supposed to be the case. In this scenario, we called our teacher to help us understand the problem with the apparatus, which is what we should also do in the future, and not to try and fix anything ourselves in case that doing so would lead to more problems than before.